Hello, so welcome to the video that is on composing Turing machines. And so here's the idea. So last time we talked about Turing machines and we implemented um, a few seemingly simple languages with them, and even these seemingly simple languages really took a lot of states to get running. And so this nickname, the Turing tar pit, arose. And the idea of a Turing tar pit is a language where really, yes, you can technically do everything, but it is so overwhelmingly complicated to do so. And nothing worth doing is remotely easy. And so Turing machines turn out to, of course, be able to do anything you could with any other programming language. And part of what this means is that you can actually implement another programming language with them. And you can use this to build up more and more complex things. And so really today we're going to look at a few different ways to use Turing machines to build up more and more complex ways of programming. And so we're going to do this in two different styles. We're first going to look at the idea of a universal Turing machine, one that we can kind of program a second Turing machine inside of. And then we're going to look at composition diagrams, which are a little bit more graphical way of explaining how TMs fit together to do some larger computation. And all of this is with the goal of maybe not getting to a full programming language per se, but giving you a sense of how to build up from Turing machines to increasingly expressive ways of computing. And so we're going to start out with this idea that an individual Turing machine doesn't need to be a complete, meaningful program. It could just be kind of a helper function to a larger computation you want to create. And as an example, one helper function Turing machine you might want to have would be a machine R that simply moves to the right. And so what that could look like, if you have an alphabet of A and B, is you have a start state and a final state that accepts. The machine is always accepting. And in your start state, you just look at all of the three characters you might have, A, B, or blank, and in every case, you move to the right. This implements this very basic abstraction of moving to the right, and does it in a way that is kind of, handles all of the characters at once by packaging together a few transitions. Conversely, you could also have a machine that does nothing but move to the left, where it has two states, and in the first state, if it sees, no matter whether it sees an A or B or a blank, it always moves to the left, and then goes to the second state that ends the computation. These are not interesting in their own, but they should be able to build up into something more meaningful. And so what are some other basic building blocks you might want to have? We could have a halting machine that just starts in a certain state and has no transitions at all and just immediately halts. We could have a machine that writes a blank in the current location. So those two states, two characters in the alphabet, no matter what is at the current location, it writes blank. And as soon as you have these basic building blocks, the natural next thing you might want to do is to compose more than one of them together. And doing this with a traditional Turing machine is a little bit uglier, more complex than you would want it to be. So if I even wanted to make a machine that just moves to the right twice, I would have three states, start in state S, have three cases each moving to the right. Go to state A, I have three cases each moving to the right, and then in F only do I finish. And what's perhaps frustrating here is if I look at the names, I may have to change the names when I'm going from one R to two. So I can't reuse a name. But somehow there's a part of this that seems to intuitively be doing the same thing twice. And so this is really screaming out, asking for some kind of abstraction to let us much more naturally take a building block, such as move to the right, and to take that building block and compose it directly and have all of the states line up correctly. If they need new names, they get new names correctly, and so on. And so what are the ways of composing different Turing machines together? So here is the proposal that I'm going to start out with. Now, a Turing machine, again, I said can be programmed. So you could have a Turing machine where its input is some kind of computer program, and in processing the input, the Turing machine will actually execute that program. And one thing we could do is we could take these building blocks like R or writing a blank or so on, and have these be the programs in a small programming language. And we can write a universal Turing machine, or UTM, that on its input tape takes in a program in that language and its input, and then runs it and actually leaves the output of it on an output tape when it's done. And this is a bit tricky to design, but it's a good exercise in understanding just how much a Turing machine really can do. All right. And so we're going to take in a program on the tape and then actually run it. And so to make this work, the state of our universal Turing machine has to be more complex. It needs to know what action it's performing next. It needs to know the position on the head of the simulated input tape. When we're deciding what action to do next, really we're going to think of this as a program counter of some kind, okay? So a pointer telling us what instruction comes next. And we're going to have a head in the tape tells us what element will be read by this next action. And so what this could look like in our tape, if I wanted to have kind of a repeated move right action, say I want to move to the right 3 times, what I could do is I could have a left marker, I could have a blank to show the start of the program. And then what I can do is in the program, it's just a list of instructions, but somewhere in that program is the instruction I will run next. And so wherever is the instruction I want to run next, then directly to the left of that, I'll have a special character, maybe the character I, that represents this is where the program counter is. And please run whatever comes next. I'm then going to have another blank to separate the program counter from the simulated input tape. And then on the input tape, wherever I'm supposed to read or write next, that is again a special character. Rather than A or B or blank, it would be the special character H. And whatever comes next is after H is the next thing I read or write. And so how do we actually program a Turing machine that takes in this tape and runs the program? So we can take some inspiration from what's called the von Neumann architecture. That is kind of the architecture behind most modern CPUs. And it's this idea that in memory, there's not a huge distinction between data and code, and that we just treat the code in there like any other data. And so what we're going to do is fetch the action we need to perform, whatever's to the right of the I, move the I to the right, and then we have a termination condition, which is that if we see there's no more instructions left to perform, we can stop. What would that look like? That would look like if there is a blank to the right of the I, because the instruction counter is at the very end of the program, the program tape. And so we can actually write out the specification for this, what it should be doing. So we could say we take in a tape that has the program, the head, and all of that. And then we're going to put the head on, and we have the head on the first position. And then the output is going to have the program counter, and it is going to have basically the output that goes with it, okay? With the head on the second blank. Okay, and we can define out, we can define out what is the program, what is the output, and then in the case U, we have a word and a value with some blank after it. And so the way that you would make this machine operate is that you're going to start out in position 1, and you're going to look for the program counter. You're going to look for the instruction. If you can't, because you finished, you halt. Otherwise, you move to the next step. You move I to the right, and then probably you're going to switch into different states based on what I is, so you can keep track of what instruction you're in. And then you're going to actually once you use the state to remember what instruction comes next. You scan all the way until you find the character H. Use that to find out what value you're applying this instruction to. Apply that instruction, update the head and the tape accordingly, and then you're going to go find I again and repeat from step 3. So find I and continue running this main program loop. And although you need to know both the program at the program counter and the value at the head position in order to run an instruction, you can just use basically the finite part of the state to remember what I was. And so you can actually write this all out as a really long transition relation. So in the very beginning, we skip over the program counter. If you need to halt, you halt. If you've run out of programs to run. Otherwise, you look for the head. Once you find the head, you actually place the head to the right. Swapping everything correctly requires a few different states. And then search for the program counter and loop again. And what we've bought through this composition is that it is no longer necessary to repeatedly implement R to copy and paste this code. By writing the UTM once and simply putting multiple R's in the input tape, you can run this instruction as many times as you want, and you can build much more complex operations out of simple operations like R. Now, this doesn't mean that it's a general purpose programming language yet, not at all. These are still clearly very simple operations. And so with the time we have left, let's look at another kind of programming language that you could write around Turing machines. Now, for the functional programmers in the crowd and for our Racket fans, you could say just use lambda calculus, just use a basic functional language rather than a Turing machine. That's a good answer too, but we call this lecture Turing machine composition for a reason. I want to talk about the idea of building up larger programs from existing Turing machines. And so we're going to do what we could think of as a Turing machine composition diagram in the style of a flowchart. And so if I have 4 Turing machines, M1 through M4, this diagram would say something like first do M1, okay, then do M2. And at the end of M2, there's going to be a conditional. If I read the character A, I go on to M3. Otherwise, if I read the character B, I go on to M4. And this still allows us to stick things together, but we now have sequential composition and we now have conditional operations, which is already feeling, composition and branching are already some things you would see in real programming languages as well. It's not quite Java yet, but it's certainly a little bit more flexible than how we started out. All right. And so, yeah. And so the CTMD, this composed Turing machine diagram, is a mini programming language with 7 different things. It could be empty. It could be a sequential composition using cons. We could be defining a label. We could be assigning a label or a name to a command. We'd have a go-to operation that jumps to a command that's already been labeled. We can have a conditional branch, which, depending on what symbol it sees, goes to different labels. And then we could also we could also have some variable operations. So defining and using variables within TMs. And so the combined TMs operation is going to allow us to compose things in this way. Okay, so it's going to take in a CTMD and an alphabet and compose it together. So if I want to define the RR machine that goes to the right twice, I'd simply use list RR to double up that command. Okay. And so another basic, seemingly basic machine that I might want to build up from this composition language would be something like move to the right until I find a blank. Because even this simple operation is now a while loop. While I don't see a blank, keep moving to the right. And so this would be find a blank to the right. And so now I'm going to have numeric labels applied to my code. For anyone that is used to BASIC or assembly language or anything like that, this is what we're doing. So we're going to have a line number 0. We're going to go to the right. And then after that, we're going to have a branch. And the branch is going to say if you see an A or an A or a B, go back to 0. If you see a blank, go to 10. At 10, we do nothing else and we're done. And so what this does is it repeatedly moves to the right by going to branch 0 for as long as there are A's or B's left to read, and then it ends when it hits a blank, finally. The same thing can be done moving to the left. You have to be a little bit more careful because you need to handle the left marker. It's not exactly the same. But at 0, we go to the left, and then we branch. If you see an A, a B, or a left marker, you keep going to the left. If you see a blank, you go to label 1 and you terminate. Now, this does mean that if you actually hit the left marker rather than a blank, the behavior would be to run forever. Because it will keep trying to go to the left and hit the left marker when really it wanted to look for a blank instead. And you now take this and start to build up some very complicated problems. So, for example, adding two numbers is known to be an extremely difficult problem in computer science that none of you have solved before. And so let's look at how to add two natural numbers, right? Which has to be so easy. First, we need to know how to represent them. And we're going to do this in a unary notation. And so what I mean by that is 0 is going to be represented by blank, and +1 is going to be represented by the character D. So if I have the number 5, I would have D, 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 D. Okay, with a blank on the end. And so in a Turing machine, if you have multiple inputs, you will often use a blank to separate them. And so the way we're going to describe this problem is that we'll take two natural numbers separated by a blank. And given this representation, there's now a way to add them, which is we want to have the same number of D's, but all in one section. And so we can fill in the blank between them to get a to get one big number, but we've added a D. So we've added 1 to the sum, and to cancel that out, we need to delete a D somewhere else. So we move all the way to the right, the last position in the second argument, and change that to a blank to get back to a total of D all in one section. And so we can now use this idea of a composed Turing machine to build something like this together. And so the phases are skip over all the things we see, all the A's we might see. Put a D in the blank. Okay. Sorry, just skip and write a D in the blank after A. Skip and move to the left. And then we're going to once we found the end of argument B, move to the left, so we're at the last position, write that as a blank, move all the way, move the head to the left. If you see a D, you're at the right position, move back to the right and halt. Otherwise, move to the right if you've found the number 0, right? Because that'll be represented as a blank. and then halt after the blank. Okay. And with these 6 steps, there's about 6 steps you're going to need, plus the start and final state for 8 states. We're not going to spell out every little step, but just to prove that it can be done, you could do something like this. So you have, you're going to move to the right. You CD, keep going to the right. If you see a blank, move to the next state. When you see a blank, go to C. See D, go to D. You see a blank, go to E. And so on. Now, how would you reason about the correctness of something like this? We're going to get into something that's really out of scope for this class, and so just treat it as a little teaser of things you could do in higher level courses and more advanced studies if you so wish. Anytime you have a program, there are special versions of logic for reasoning about the correctness of programs, a common one being called OR logic. And what you can do is for each rule in the Turing machine, you can have a correctness precondition and postcondition. Okay, so some assertion that's told before and after running that rule. Then prove that these specifications hold. Prove that if this in the beginning, then this in the end. Not entirely unlike what we had for invariants. Okay. But to actually go through and do it would be quite a lot of code. So we're not going to go through every step of this proof, but I'm going through it just to show you a few more things we can do. So another example of machine you might write is called a copy machine that just goes through and takes a given word, writes the same word after it, inserting a new blank at the end after the word that it is copied. Okay. And so what is interesting about something like this is that it's something that you would actually be able to build up using these operations from before. So something like copying a word would be broken down as finding a blank to the left, moving to the right, checking what character you see next. And if it's a blank, find a blank to the right, move to the left. Right, and so, or if you find an A or a B, you need to write a blank, find a blank to the right, find a blank to the right. All right, okay, go to blank to the left, blank to the left. Okay, we're back to the loop. And you don't need to understand every line of code, but I hope that even looking at this diagram can help us appreciate the possibility of building up much larger, much more complex computations from these simple pieces. Okay, and actually proving the correctness of this is a bit beyond scope for what we are planning to do in this course. And so we are at the end of this set of slides, and we're going to come back and talk next time looking at Turing machine extensions. All right, have a great rest of your day.